enthusiastic of India. Your minds are fuller with ideas, perceptives, and insights. Today also, we continue this enriching journey of knowledge sharing. Today's session focus on innovation and sustainability. Please join me in warmly welcoming Dr. Neeraj Kumbhakarna, Associate Professor from Department of Mechanical Engineering, IIT Mumbai, Maharashtra State, for Session 9 of 5th day. This session explores the topic formulating rocket propellants for the future with a focus on sustainability and environmental impact for sustainable development. So on the behalf of PS College of Engineering, Chhatrapati Sambhajinagar and organizing team, let us extend a warm welcome to Dr. Neeraj Kumbhakarna sir. I invite Dr. Kakde sir to introduce him. So over to you.
Good evening to all participants. On 5th day of this AICT training and learning, sponsored online FDP on strategic implication of energy efficiency, conservation and sustainability for global competitiveness, organized by IQSCL in association with Department of Civil Engineering of PS College of Engineering, Chhatrapati Sambhajinagar. Today on 9th session, we have with us Dr. Neeraj Kumbhakarna. He will be shedding lights on formulating rocket propellants for the future with the focus on sustainability and environmental impact for sustainable development. It is my privilege to welcome Dr. Neeraj Kumbhakarna sir. He is currently working as an associate professor in Department of Mechanical Engineering at Indian Institute of Technology, Bombay. He has completed B in Mechanical Engineering from Government College of Engineering, Chhatrapati Sambhajinagar, and ME in Mechanical Engineering from Indian Institute of Science from Bangalore. He has obtained his doctorate from Pennsylvania State University from United States of America. The topic of his PhD was combustion studies of novel energetic materials. The focus of his doctoral thesis was on the identification of the initiation and secondary reactions occurring during the thermal decomposition of novel nitrogen energetic materials. His present research focus experiments and simulations involving combustions and decompositions of energetic materials. He has 50 peer-reviewed journal publications to his credit. He has currently hold the position of Associate Dean, Infrastructure Support and Planning at IIT Bombay. This is what the short introduction of Dr. Neeraj Kumbhakarna sir. I request him to start the session.
Thank you, Dr. Kakade, for the introduction. I hope I am clearly audible.
Yes.
Yes, so you're audible.
Yeah, I will just share my screen so that presentation can be seen. And I hope that my screen is also visible.
Yes,
Yes,
the
yes.
screen is also visible.
Okay. Is it clear? Am I not? I'm sure I'm. I hope I'm not blocking the view here. Can everyone see the screen and read the matter?
Yes.
Oh, great.
We are able to read the screen.
Okay, thank you. Yes, so I thank the organizing committee members of this program to give me an opportunity to speak over here. The theme of this workshop, this faculty development program, is on sustainability. So that is what we'll talk about. My primary research is on rocket propellant. So when Dr. Kakade, he was talking about energetic materials. Energetic materials are basically materials that generate a large amount of energy when they are burnt. So you see energetic materials here. So I currently am in charge of the energetic materials research laboratory here at IIT Bombay. Energetic materials, as I said, they are materials that generate a large amount of energy very fast when they burn. So we can't really call petrol or diesel energetic materials. They do emit a large amount of energy when they burn, but they don't emit it fast enough. The rate of energy emission is very slow in their case. Hence, we don't call them energetic materials. Energetic materials are typically used in rockets to fuel rockets, because in rockets, the fuel has to burn very fast so as to generate the high pressure gases, which can be ejected through a nozzle and to give you thrust. And energetic materials are also used in explosives. So explosives either for military or for civilian purposes, where they are used for controlled demolitions and things like that. Now, when it comes to energetic materials, where the sustainability comes in. See, as compared to other engineering applications, in energetic materials, sustainability typically takes a backseat. Because now, as I said, I'm currently working in rocket propellants. Rocket propellants are used to drive rockets. Rockets are primarily used in two applications. Uh, this Diwali rockets and all is not a very primary application. Primary application is rockets for space exploration, for space journeys, space vehicles. Second application is rockets that carry warheads. So all these missiles, which the military uses, they are rockets. The first priority for these rockets would be to accomplish their mission. So if you are going to destroy an enemy, your mission is to destroy an enemy targets, the rocket should be able to do that. Sustainability, if environmentally it's a little detrimental of or it's causing some environmental pollution or some other problem, that is secondary. Typically, that is how it has been looked at. Sustainability in everyday applications such as automobile, cars, engines, means of transportation, and other things. Appliances such as refrigerators, air conditioning. Sustainability takes a front seat. It's primary. But in energetic materials, especially with regard to rocket propellants, sustainability takes a backseat. Nonetheless, it is important. So what I'm going to do here is I'll talk about some research that we did in the last few years by taking one particular example. I'll talk about what kind of research techniques we use to accomplish the objective. So what our objective was, see, when we talk about rocket propellants, rockets are propelled by various means. You have electric propulsion, nuclear propulsion, plasma propulsion, many different types of propulsions. But primarily, as of now, and I envision that for the next many years, chemical propulsion is going to be the primary means of propulsion. Chemical propulsion means you use some fuel, burn it, generate high pressure gases, and propel the rocket. There are other means of propulsion where you use nuclear reactions to propel the rocket, or where you use plasma to rocket. But those are still in very early stage of development. There are a lot of issues with them, hence they are not really feasible to be used on a large scale. Primarily, when I say propulsion, what I mean is chemical propulsion. And then there are two types of chemical propulsion, solid and liquid. There is also a third one, hybrid, which the technology is still in incipient stages, has not yet fully developed. So how a rocket works is you have a combustion chamber and you have a nozzle. And if I particularly talk about solid propellant rocket, you have a combustion chamber where you have this fuel, this rocket propellant grain, as they call it, and it's that grain is actually integrally fixed, casted into an engine casing, and then you use an igniter. That igniter can be fired using another fuel, or can be operated using electricity or something like that. It's basically a source of heat that will ignite the propellant. The propellant will then burn, so it will start burning from inside to out. So this is the burning surface, and the burnt propellant will be in the form of gas, which will generate a large amount of gas, and it will generate very high pressure, which will be ejected through a nozzle, and it will propel the rocket. Now, this fuel is basically a combination of two things, fuel and oxidizer. In a rocket, typically cars, automobiles, they will use external air. They will use oxygen from the air to burn the fuel. But we can't do that in a rocket, because extremely high amount of oxygen is required at a very high rate. So atmosphere cannot supply that oxygen. So in solid propellant rockets, oxidizer and the fuel are mixed together and they are casted into a solid, and then the chemical reaction, the burning happens, it's self-contained. You don't need to supply oxygen from outside for burning. So fuel, there are many different types of solid fuels for rockets, HTPB, then this PBAN and many others, solid rocket fuels, GAP, glycidyl azide polymer, many fuels are there. And oxidizer. So oxidizer does not necessarily mean that you have to give oxygen. See, for burning, you don't necessarily just need oxygen. You need any molecules that contain oxygen. That is also good enough. Or even oxygen may not be, even oxygen is not something that's really necessary. Or just oxygen is very common oxidizer, but there are others which do the job of oxygen. For example, elements that are on the right columns of the period have a high oxidation number. So if you look at the periodic table on the right side, where the oxidation number increases from left to right. So these elements such as fluorine, chlorine on the right side, where oxygen is typically also on the right side, atomic number 8. So that those elements can act as oxidizers. So here, by far, for the last 50, 60 years, all the time when human beings have been using solid rockets, the oxidizer that has been used is ammonium perchlorate. Is a very, very commonly used oxidizer in almost more than 90% of the rockets, space, defense, missiles, anywhere. The oxidizer is ammonium perchlorate. So this is basically a salt with the positive ion as ammonium, so NH4, NH4 and ClO4, perchlorate. It's a perchlorate salt of ammonium. Here it has 4 oxygen atoms, hence it is an oxidizer. It also has a chlorine atom, which is also an oxidizer. Chlorine also is on the rightmost column of the periodic table. It's a halogen. Now the problem with this ammonium perchlorate is that it has chlorine. So when you burn it, chlorine is released into that. And we know that it's harmful, ozone depletion and other things. It's a toxic chemical. Now, as I said, see, it's not that important because anyway, you're firing rockets to destroy things. So why worry about it? Is one school of thought. But now when sustainability, environmental pollution, it becomes increasingly important. People have started looking for molecules other than ammonium perchlorate, which can be used as an oxidizer. Why is ammonium perchlorate so great? Why is it used everywhere? Is because, yes, it's a good oxidizer. Other than that, it has a lot of very favorable properties to be used in rockets. It can be casted very easily. It has very good mechanical properties. It has very good moldability. It reacts very fast. Its reaction rates are high. Many things. That's what makes it a very good solid propellant oxidizer. And now when we start to talk about sustainability and things like that, environmental concerns, then the problem would be, the case would be to now come up with a molecule, come up with an oxidizer which does not have chlorine. So this is a challenge. And how would you accomplish it? Now, if you just start to think, okay, I want to make a new oxidizer, how will you do it? You first have to imagine a molecular structure which will have similar properties to this, but will not have. That has to be then studied. You have to first make sure that it will indeed give you the energy that ammonium perchlorate gives. It will indeed perform. You cannot just so the weight of the fuel in a rocket is anywhere between anywhere between a few thousand kg to several tons. A huge amount of fuel you need in a rocket. Now make several tons of the new fuel that you thought of and fire it in a rocket. That's not how it works. You'll first have to make sure that whatever molecule you have thought of performs the way you want it to perform. Only then you can put it in a rocket, fire it. So there is a long way to go by just starting to think about making a new oxidizer to actually realizing it. So I'll just go through those steps. I'll just go through those research techniques which you typically use by taking this ammonium perchlorate as a case study. So how we went about solving this problem and what experimental techniques and computational techniques we used to solve that problem. So we will just go through that. And that's what I meant when I said, okay, development of solid rocket propellants with sustainability. So how do we develop a rocket propellant? The sustainability factor that I have already mentioned is we want to get rid of this chlorine atom, right? So main research aspects that one needs to do here is, one needs to go through is, first of all, you need to think of a molecule, a stable molecule that will perform uh, as per your requirements. So for that, you have to do what is called as molecular modeling. So all of us know computational modeling. Typically, when we do computational modeling such as CFD or FEM, we are in the continuum regime. We solve conservation equations in the continuum regime. But when you want to study molecules, that may not work. We'll have to go to the quantum region where the molecular forces can be looked at. So we, in our energetic materials research laboratory, we do quantum mechanics based molecular modeling where we study molecules. So now, okay, I want a molecule which does not contain chlorine, but which has to be a good oxidizer. So it should not contain chlorine, but it should contain oxygen. That is one thing. Then it should burn very fast, because if it burns slow, then the energy release will be very slow. It will not be a good enough property. It has to burn very fast. Then there are some other properties. For example, it has to have a high density. If it has a high density, then in the small volume of the rocket combustion chamber, I can pack a lot of material, lot of oxidizer, because that is a requirement. Then it should also not be toxic. Then it should not be corrosive. All these things. So so I have to think of some molecule. So we can use our elementary knowledge of chemistry of how molecule atoms combine together, and then we can develop, and then we can do the quantum mechanics modeling for that. What do I mean by this is, then like we have conservation equations to solve for normal FEM or CFD modeling, we have to solve the Schrodinger's equation for a molecular system to do quantum mechanics modeling. When you solve that equation, it basically is a force and energy balance between the various attractive and repulsive forces of electrons, nuclei, and protons in a molecular system. So when you do that, you will get an optimized molecular structure of the molecule that you have envisioned. And then you can study how it reacts also, because see, you have to, through molecular modeling, without making the actual molecule, without getting the actual molecule, before we actually realize the molecule, we can predict its properties, we can predict how it reacts. Because once you solve the Schrodinger's equation for that molecular system, we'll not go into details of what that equation is and all, because that's a subject in itself. So we'll superficially discuss this. So once you solve the equation and develop the molecule, you develop the molecular structure, you can predict any of its property, because that Schrodinger's equation gives you the wave function of the molecule. That wave function is basically the DNA of that molecule. It can tell you everything about it. So on the computer itself, without realizing the actual molecule, we will study the properties of the molecule that we have envisioned as our new oxidizer. Then we will have to see whether it actually gives you that performance. So then we will, once you have studied the molecule, once you know the chemical reactions that it undergoes, because you develop the reaction mechanism through molecular modeling, you can then go into continuum level modeling, where you can model the combustion of that molecule, and you can predict what kind of specific impulses, thrust, forces, energy, temperature it will give. Once that is done and you're satisfied that, okay, whatever I have imagined, whatever molecule I have imagined, now performs the way, at least through modeling, numerical prediction, it performs, numerical simulation, it performs the way I want it, then you actually go to the lab, to the chemistry lab, then go through the reaction, sequence, do all these reactions and produce a small amount of that molecule, because that has to be done. The molecule has to be produced in a small amount in the lab, because you cannot produce several tons of it immediately. That's too much money, and you don't know how it will predict. Although on paper it seems to predict well, on the actual rocket, still there is a lot of difference between theory and practice. So you have to make it in small amounts, then test it in the lab. And then I'll talk about what are these different experimental tests that we use in the lab to test it. So burn rate, flame temperature, soot measurement, and these kinds of things. And once we have done these tests and it confirms to what we wanted, then we can go to the industry for large scale manufacturing and testing. Right. So we will look into the details of these processes first. So when we started thinking about oxidizer molecules, we thought about several molecules. Like we analyzed about 100,000 different molecules through testing, through molecular modeling. And then we came up with these 6-7 molecules. So this is ammonium perchlorate, and these are the 6 molecules. And then we predicted their properties, as I just said, and then we compared them. So what will make a molecule a good oxidizer? So by the way, see, these molecules is something that we have imagined. We have just thought of these molecules. These molecules did not exist before. These chemicals were not there before. So we thought that maybe these are the molecules that can give you the performance. So we looked at their performances. We saw that, okay, the oxygen. So what is the characteristic? Like why would a given molecule or a material be a good oxidizer? It will be a good oxidizer if it has a high oxygen balance. What do you mean by oxygen balance? Is the oxygen that is contained in the molecule should be able to come out of the molecule and burn the fuel. See, if the molecule has a low oxygen balance, like for example, if it has 0 oxygen balance, that means all the molecule will go into burning that compound itself. So that compound, say ammonium perchlorate has nitrogen, so nitrogen and hydrogen. So this oxygen, if it goes into burning the hydrogen and nitrogen only, then we don't have anything left to burn the fuel. So 0 oxygen balance means that all the oxygen burns the molecule itself. That we don't want. We want a high positive oxygen. Ammonium perchlorate has an oxygen balance of 34, very, very high. Very few molecules will have that high oxygen balance. So we came up with some of these molecules where one had 26.2, the other had 20.1. So not as high as ammonium perchlorate, but will it still perform better or equivalent to ammonium perchlorate? Let us see. Then we calculated the density. Now we don't have the material. How can we calculate the density? We can. If we can do molecular modeling by looking at the molecular structure, it's possible to predict the density. So ammonium perchlorate has a density of 1.595 grams per centimeter. A lot of these molecules are very close to that. You can see here. Heat of formation is another property. Heat of formation is basically how much energy is packed into that molecule. It's a measure of energy packed into the molecule. So heat of formation for ammonium perchlorate, it's not easy to calculate because it's an ammonia ionic compound. But for these, it can be calculated, and we can see that higher the heat of formation, the better. So some of these molecules have a very high heat of formation. This is decomposition temperature. Means when it burns, at what temperature does it decompose? So decomposition temperature for ammonium perchlorate, if I remember it correctly, is somewhere close to 500 Kelvin, which is 220 something degrees Celsius. So it should have a high decomposition temperature. Otherwise, it will you have kept it in your room, it will decompose. So that's not what you want. So some of these compounds, this one S11. Now I'm calling these S11, S15 because these compounds were not there. They did not have any names. So we were just given them some names. And then you can see this S11 has a high decomposition temperature, even higher than ammonium perchlorate. So this is a good compound. So we found some of this did not have a very high decomposition. So we may not be able to use. Then there are some of these quantities, nozzle exit velocity, C star velocity and all. We'll not go into what these are. We will look at this so these are the electrostatic discharge sensitivity or impact sensitivity. So sensitivity means impact sensitivity means does the compound trigger on impact? Like if you hit it with a hammer or something, does it explode or does it ignite? So that is also the impact sensitivity should be high. Impact sensitivity should be low. It should not impact. It should not impact on ignite on a small impact. So the higher is this number, the lower is this impact sensitivity. So these impact sensitivity numbers are actually good. So we will not get into what is a good number, what is a bad number. You'll have to take my word for it. And then electrostatic discharge sensitivity is how sensitive it is to electrostatic discharge. So that sensitivity should also be low. Then most important parameter here is ISP, specific impulse, which is the thrust. If you put this oxidizer in the rocket, fire the rocket, what is the thrust force generated by? So this is a measure of performance of the propellant. Like for a petrol or for diesel, good quality petrol or good quality diesel means the measure of performance is kilometers per liter or miles per liter, mileage. High mileage means good fuel. So here high specific impulse means a good rocket. And you can see ammonium perchlorate has 264, whereas some of these compounds have much higher ISP. So these are definitely, if we can realize these compounds and we use them in our rockets, that would be great because these are much better. And this is rho ISP. Rho ISP is a multiplication of rho and ISP. That is because the denser the compound, the more you can put in the rocket. So that's advantageous. So this some of these compounds have a higher rho ISP than ammonium perchlorate. And then yeah, this is oxidizer aluminum percentage. This is also an important parameter. Homo-lumo gap, we will not get into what it is. So now our theoretical studies, our molecular modeling studies, we have come up with some molecules which seem to be better than ammonium perchlorate. What is the next step? We have to make these molecules. So yes, and then yeah, these are also these are the same molecules that I showed you on the last slide. And there are some, these are some of the additional properties that we need to look at because oxygen balance, density, heat of formation, we discussed all this. But then, yeah, metal to non-metal ratio, is it metallic, is it non-metallic? We typically will prefer non-metallic. And then impact sensitivity, friction sensitivity, yeah, and then vacuum stability. So it should be stable. If it's not stable, then it's useless because when it is transported, stored, it should be stable. And then overall yield in number of steps. What is this? So this is basically, now as I said, we know which molecules, we have found some good molecules, we have to make them. So you have to come up with these reaction schemes and go to the chemistry lab. So our energetic materials research laboratory has all the chemistry equipment, the fume hoods, rotavapors, and all the chemistry equipment to make these molecules. So you have to use a raw material and you have to go through several steps. So for example, this is like DMF reflex is a chemical process. You have to, this reaction is to go on for 24 hours and it gives you a 70% yield, 75% yield. What does that mean? That means that starting material, if you use 100 grams, you will get 75 grams of this material. Like this is called as a yield. So actually, if you go on doing this 75%, 35%, 12%, you will get very little of the final compound. So this is something that also is important. Yield should be high. And if you look at this, the yields 10%, 30%, 13%, 10%, 19%, 15%, 54%. So these are the yields that once you start from 100 grams of the starting material, how much finally product you get. So these yields should also be high, or we'll have to check whether these yields are economical. Is it economical to make the compound with these yields? So this is the issue. So now we'll proceed. So this is the chemical pathway, synthesis pathway as we call it, for the, excuse me. So this is the chemical synthesis pathway for some of the compounds. So this pathway, chemical pathway for this compound. So to come up with these chemical pathways is also challenging. We have to see, this is the final structure we want. So to make this, which should be the starting structure, what are the different chemical reactions we should go through? So we should have knowledge of these various chemical reactions, pathways, substitutions. So it's a challenging process. So we typically collaborate with professors in the chemistry department over here. One of the professors, Professor Namudiri, helps us with this. And then you can generate, you can create these molecules. So see, everything is we should not lose track of our main goal, sustainability. Everything is being done from the point of view of that. We want a molecule which does not have chlorine and which will be a good rocket. So there are various chemical. We won't go into again details of these, but just to show you, these are the chemical processes that we use to generate these molecules. Now, once they are generated, typically they are made in small quantities because these are highly inflammable, highly reactive molecules. Handling them in large quantities is dangerous. So in the lab, we can make them only in small quantities. Now we have a laser. We have made them in small quantities. The next step is to analyze, to study them, to see whether they perform the way we want. So first thing we will have to find out is what are the products that are generated when these burn. We don't know, so we have to see that. Second is how fast do they react, because the chemical reaction, okay, they are good, they have a high oxygen balance and they have all good properties, but when we actually burn them, if they burn very slowly, then the rate of heat generation will be very slow. So we don't want that. We want them to burn fast. So we will have to find out the rate of chemical reaction of their burn. So for that, what we do is we have developed. So this is experimental setup that we have developed in-house of course by purchasing various equipment components. But this is not something that you can just buy off the shelf. This is something that we have developed for accomplishing this. So what is done here is you have a laser beam. That laser beam through a system of lenses and mirrors is targeted onto a small sample of the oxidizer we have developed. And then because of that highly concentrated laser beam, the sample burns. It burns and it generates the product gases. And we also we use only very small 1 to 2 milligram of the sample of the propellant oxidizer. And when it burns, we continuously measure the mass because it burns and turns into gases. Its mass reduces. We continuously measure the mass every 50 milliseconds. So we have a very high precision microbalance, which is here. The microbalance tray is kept inside the pyrolyzer, and that mass is measured continuously. And if the mass falls very fast, that means the reaction is very fast. If the mass goes down slowly, that means the reaction. And then, of course, when it burns and the gases come out, these gases are analyzed by an FTIR spectrometer. FTIR spectrometer is an instrument which tells you that what are the product species that are there in that gas. So now we know what product species it is producing, and we know how fast it is burning. So then we can we can find out the chemical reactions that are taking place, because you know the reactant, you know the products, and you know the rate. So the chemical reactions in the rate we know. So now we have we do that, and we find out, we make sure that it burns fast, or we check whether it burns fast. So this is a novel tool. This is called as a laser pyrolysis chamber that we have developed to predict the chemistry of decomposition and the rate of decomposition of any molecule, any chemical. It's capable of measuring mass and decomposition products simultaneously under combustion-like environments. Now, this is important. Why did we have to develop this apparatus? Because such apparatus for measuring mass and decomposition products, standard equipment is available in the market, but that cannot do this carry out this measurement under combustion-like environment. In the rocket, the environment is, the heating rates are very high, the pressures are very high. So those instruments don't have that facility. Hence, we built this so that we can use a laser. It's a 400-watt, very high power laser, which burns the material very fast so that you can simulate the conditions inside the rocket. So we use this to analyze the chemistry, the chemical behavior of the newly developed oxidizer molecules. But that is not enough. This is just a schematic of the laser pyrolyzer. So that laser beam comes here. It is reflected through a mirror. This is the sample holder. It's basically an aluminum foil on which it is resting. This is the microbalance, and the laser beam falls onto the sample, and then it goes to a laser dump here, because it has to be dissipated. The laser heat has to be dissipated. Otherwise, everything will get heated. This is the pyrometer window through which the sample is analyzed using the FTIR. This is the FTIR window through which the FTIR beam passes and does the analysis. So this is a schematic of this pyrolysis chamber. This is the pyrolysis chamber. This is a magnified version. Now, the another issue is we have found out the rate of chemical reactions. Now we have to also calculate the burn rate. The burn rate is how fast, at what rate the chemical burns. So if you take like a rod of that material and if you ignite it at one end, how fast it burns. That is a very important parameter for rocket propellant. It should burn fast. So how do we measure the burn rate? So what we do here is we suspend the material at the end of a quartz rod. We ignite it using a spark, and then we do high-speed photography of this to analyze how fast it burns. This is one way of doing it. And then secondly, see, as I say, another important parameter for this is flame temperature. So when you ignite the propellant and when it burns, what is the temperature of the flame that is generated? High temperature means high energy. Flame temperature is desirable. So, but the problem is if you want to measure the temperature without disturbing the flame. You can use a thermocouple or some instrument which you can put in the flame and measure. But here, if you do that, the flame will get disturbed. The combustion characteristics will change. We don't want to do that because we want to predict the correct combustion characteristics as well as measure the temperature. So we use we have developed a process to measure the temperature without touching the flame. We do have we do have instrument to measure temperature without touching. Like in the COVID time, we measure the temperature of the person without touching by that thermal gun. But that can't be used here because you see, flame is basically a gas. It's not a solid surface. The instruments that we have available in the market for measuring temperature without touching can perform very well when the surface is solid. But for gas, they don't do very well. Why? Again, there are a lot of reasons for it because you have to know the emission properties, the emission properties, dispersion coefficients, and a lot of other things you need to know to be able to predict the temperature correctly. So we developed the procedure for measuring the flame temperature using a consumer grade DSLR camera. We don't need a very hi-fi camera. We need a consumer grade DSLR camera for this. We have developed that method, how to do that. So basically what we do is we take photos of the flame and then we do some back calculation using laws of radiation and other laws. And then we have developed an algorithm so that the temperature can be back calculated from the photograph of the flame. So this is a photograph of the flame. And this is our algorithm working on it. You can see that these colors denote temperature. So green means 1500 degree. This orange means 1900, like that. And for this flame, for the central region, you cannot measure the temperature. That is because the rod is present here. And also, this temperature prediction can only be done within a certain range. If the temperature is outside that range, this method will not be able to measure. We are working to enhance the capabilities of this method, but right now we have to go with what we have. So now, another important parameter to measure is what is called a soot concentration. See, when a material burns, it will generate these black carbon particles called soot. This is basically unburned fuel and some aromatic compound. It is not desirable. Fuel, if a good fuel is there, it should not form soot. So now we have developed this fuel. Before scaling it up and putting it in actual rocket, it is essential to measure the soot concentration in its flame. So this we have developed a method for measuring the soot concentration also, which we call as the light extinction technique. It is not a new technique. The technique existed before, but we adapted it to our method. This temperature measurement using consumer grade DSLR camera is something that is developed by us, but this is not something we have done. This is there, we have adopted it. So here our technique produces images like this, where the magnitude of the darkness or the shade of this is a measure of soot concentration. And so we can numerically calculate the soot concentration from this image. This is how it is done, is laser extinction. So basically you pass a laser beam without igniting the fuel and take the background image, then pass a laser beam after igniting the fuel. Some of the laser will be absorbed by the soot. So after ignition with soot present and before ignition with soot absent. That ratio is a measure of how much radiation, how much laser energy has been absorbed, which is basically a measure of the soot concentration. Higher soot concentration absorbs higher energy. So this is the schematic of how we do this temperature and burn rate measurement. So this is the combustion chamber. Here, this is the quartz rod. Here, the droplet is suspended, and DSLR cameras are there on both sides of the perpendicular sides of the combustion chamber. This is a backlight to measure the burn rate. There is no backlight here because here we want to photograph the flame. So this camera photographs the flame. This camera photographs the droplet. And this has to be connected to a vacuum pump because it has to be continuously vacuumed after the experiment. And this is this ignition transform. It's a transformer to generate high voltage so that the spark can be generated to ignite. And this is a switch. So this is a setup that we have developed. These are some of the photographs when the flame is burning, because these are propellants. They burn very fast. The flame looks like kind of violent, very vigorous. It doesn't burn like an ordinary candle. It burns very vigorously. And then, yeah, these are some quantitative measurements of how fast it burns. So this is the droplet, the diameter of that fuel sample at the beginning, and then this is how it varies with time. So again, quantitatively, we'll not discuss this because for the lack of time and also getting into too much technical details, we'll have to have a separate lecture on that. Right. So these are some of the results. Again, no need to go into it too much, but we can see that the flame temperatures that are produced are quite high, which is good. We want high flame temperatures. And then this is the laser extinction setup for measuring soot concentration. So you have the fuel droplet here and the laser and the camera here. Right. So this is the photograph of the laser extinction setup. So the laser comes from here through a system of mirrors and lenses, goes to the combustion chamber and falls on the zoom lens of the camera, CCD camera, charge coupled device camera. Yeah, I'll skip through some of these slides. Now coming to the final this thing. I said we started out with 1,000 different molecules. We found explored many of them. Computationally, we zeroed in on some 5-6 molecules because we cannot produce 1,000 molecules. That is too expensive and too tedious. So computationally, we have to study those molecules and only identify the ones which gives good properties when predicted using computational methods such as molecular modeling. And only those we made. We made some 10, 12 compounds, and we found out that once we started analyzing them for soot concentration, temperature measurement, as I showed you, reaction and all, we found that these 3 are good. So these 3 have a high oxygen balance, they have a good high chemical reaction rate, they have good high flame temperatures, so they are good in all respects. So that then we have to, so these we have now applied for patents on these because, as I said, these molecules did not exist before. Now the plan is to then give them to DRDO. So this HEMRL, High Energy Materials Research Laboratory, is a DRDO lab which works on making these such energetic materials. We'll give it to DRDO. The DRDO will get them scaled up. So they'll outsource it to a company and produce them in large amounts, then test them in missiles. So that remains to be seen. But I think we are very hopeful that given all this work, these materials would be good substitute for ammonium perchlorate, and these don't have chlorine, so that environmental issue is being addressed. And in addition to oxidizers, we also worked on some binders. So see, as I said, solid rocket propellant is not just oxidizer. It is oxidizer, fuel, binder, and there are some other things also. So binder is basically something that binds the oxidizer and the fuel together and gives you a good solid propellant block. So binders also, like there are some properties that are important for oxidizers. There are some other properties that are important for binders. So the similar study was done for binders also, and we came up with 2 good binders. We have also applied for patents for these. So, see, this is the process. This I just described the process of how you go about developing rocket propellants with an intended objective in mind. Here, the objective was to get rid of the chlorine. Now, the issue still remains is, see, we analyzed, we started with 1,000 molecules and zeroed in on just 3 molecules. We started out with 1,000 molecules based on our elementary knowledge of chemistry. The question is, did we explore all the space? Did we explore all, we look at all the atomic combinations that are possible? Of course not, because infinite combinations are possible to generate good molecules. Now, how will we do that? Manually, the human brain has limitations. It cannot imagine infinite combinations. So the argument is, yeah, we have come up with these 3 good molecules, but we may not have analyzed or explored the entire space, which will give us the best molecule. So what is the answer? How would we do that? How would we analyze a large space and intelligently come up with good suggestions for testing good molecules that are likely to be good oxidizers? The answer to that, of course, is like it is to a lot of technical problems today in artificial intelligence, machine learning. So now we are also working on developing a machine learning model which will browse through the whole large number of almost infinite number of combinations and will generate a model, molecules for us. So this is a generative RNN. It's called as a recurrent neural stack augmented recurrent neural network, stack augmented RNN. It's a particular type of machine learning model which serves this purpose well. So that model will generate a molecule. I'll not go into the details of how exactly it generates that. There is a whole process, but it generates the molecule. Then we will calculate the oxygen balance of the molecule that has generated. And if it has good oxygen balance, we will reward it. We will give it a positive reward. And then we will feed this data. We will feed this reward data back into the generative. So it is like, this is called as reinforcement learning. Reinforcement learning means the machine algorithm learns by through reinforcement. So if it gives a good result, we reward it. So then in future it will give even a better result, an even better result. If it doesn't give us a good result, we give it a negative reward. So it knows not to go in that direction. So if you go through several iterations of this, it's possible to generate oxidizer molecules which are good. And once this machine learning model gives us some good molecules, they can go through the same analysis that we perform for these other molecules. Right. So this was the process. This is what I wanted to share with you. This is the work that we are typically doing. We are also doing working in some other areas, but this is our primary research area in the energetic materials research laboratory here at IIT Bombay. And I hope I could add value to this faculty development program. And again, I thank you very much for inviting me and giving me this opportunity. And now we can go on to any questions that you might have. So that
I request participants to please ask questions. You can even put your questions in chat box. Chat box. Participants, if you have questions, you can please ask.
yeah, they have the right to put this thing, right? Participants have the right to type in the chat box?
Yes.
Okay. Yeah. Sometimes you have to give them through this Zoom system, you need to give them the rights.
So I think we don't have questions for the session.
Okay.
It was a great session, Dr. Neeraj,
Thank you.
and it's after such a long time hearing you face to face. Actually, not face to face, but screen to screen.
Yeah.
Sitting
So,
side by side to facing screen to screen. It was great hearing you. Could get the knowledge of rocket propellants, molecular modeling, various synthesized compounds. It was great to hear to you. So now I request Professor Monday to please propose the vote of thanks.
Thanks, sir. Thank you so much. And thank you, Dr. Neeraj, sir. Good evening once again to everyone. It is my honor, really honor and pleasure to deliver the vote of thanks on the behalf of PS College of Engineering, Chhatrapati Sambhajinagar, organizing committee. First and foremost, I extend our heartfelt gratitude to Dr. Neeraj Kumbhakarna for the insight and thought-provoking session on this such a complicated topic of rocket propellants and its sustainability. Sir, your insights, your expertise in the field of rocket propellant and your ability to bridge the scientific concepts with real-world applications have truly enriched our understanding of propellant technologies, their current challenges, environmental implications, and the path forwarded towards the sustainability alternatives. So really, it was a very wonderful session hearing from you. You offered a fascinating look into the balance between the performance, safety, and environmental responsibilities too, reminding us that the innovation in aerospace can and must go hand in hand with the sustainability. We truly appreciate the depth of knowledge and the clarity with which you presented such a complex topic. Thank you so much, sir. I too thank to our participants for their keen interest and understanding this topic. Thank you.